In this presentation, we're going to consider a couple of calculations that are typical examples of what you can expect in the pre-registration exam of 2020. The first question is from Domain 1 and on Competency Standard 1.4, and it is on health economics. So this question concerns the cost saving if you compare ciprofloxacin administered via the intravenous route versus the oral route. And the oral route looks like it's going to be the cheaper route. And the question asks you to calculate the cost saving. So we're going to take a look at the approach on this calculation. In your approach on this calculation, please note that for both routes of administration, it is a twice daily regimen. So the dose is administered every 12 hours. So the approach that we followed here is to calculate the quantity of drug that is needed for a 24-hour cycle. So for the intravenous route, that will be 800 milligrams, and for the oral route, that will be 1,000 milligrams. The next step is to calculate the cost for the 24-hour treatment, and that comes down to 48 Rand for the intravenous route and 11.80 Rand for the oral route. And the way that this was calculated was based on the information given in the question. The question states that for the intravenous route, the cost of treatment is 12 Rands per 200 milligrams of ciprofloxacin. And for the oral route, it is 2.95 Rand per 250 milligrams of ciprofloxacin. So in order to calculate the cost saving, you have to subtract the cost of the oral route, which is 11.80, from the cost of the intravenous route, which is 48 Rand. So the saving is 36.20 Rand, and you will see that's option C from the list of options given. The next example comes from Domain 2, the safe and rational use of medicines, and it is on Competency Standard 2.3, Patient Medicine Review and Management. Let's start off with reading the question. Medicine X is administered at a recommended flow rate of 3 milliliters per minute when used at a concentration of 5 milligrams per ml. Medicine X is only available in 500 milligram vials for dilution in a 5% weight per volume glucose solution. The IV administration set is calibrated at 20 drops per ml. How long will it take for the total volume of fluid to be administered? In approaching this question, please note the following: that the flow rate required is 3 milliliters per minute, and this flow rate is applicable to a solution with a concentration of 5 milligrams per ml. What you have available is vials of the medicine containing 500 milligrams. So you have to dilute it to a concentration of 5 milligrams per ml. So if you have 500 milligrams, and to get it to a concentration of 5 milligrams per ml, you have to dilute it to 100 milliliters. If you then have it at the correct concentration of 5 milligrams per ml, this preparation can be administered at a flow rate of 3 milliliters per minute. So if you have to administer 3 milliliters in 1 minute, 100 ml will therefore be administered in how many minutes? And that will come down to 33.3 minutes to administer the total of 100 milliliters. The following question comes from the same domain, domain 2, but this one is on competency standard 2.4. That is medicines and medical devices safety. So let's start off with reading the question so that we can see what's given and what is required from us. Zinc sulfate 0.25% weight per volume eye drops are required to be made isotonic with sodium chloride. What weight of sodium chloride is required in the preparation of 100 milliliters of eye drop solution? And then important on this question, there is some additional info given, and this info is important. The information supplied reads as follows. A 0.25% weight per volume solution of zinc sulfate depresses the freezing point of water by 0.022 degrees Celsius, and a 1% weight per volume solution of sodium chloride depresses the freezing point by 0.576 degrees Celsius. An isotonic solution freezes at minus 0.52 degrees Celsius. So let's start off with what type of calculation this is. This is clearly an isotonicity calculation, and based on the information that was supplied, this is a freezing point depression calculation. And the moment you hear freezing point depression calculation, you can recall the following equation that will be applicable to doing this calculation. The formula applicable is W equals 0.52 minus A divided by B. Now, before you start using this formula and do the calculation, you need to know what the symbols stand for. Let's start off with the A. The A will be the freezing point depression of the solution at hand, and B will be the freezing point depression of a 1% weight per volume solution of your adjusting substance. In this case, based on the information supplied, the adjusting substance will be sodium chloride, and the freezing point depression of a 1% weight per volume solution of sodium chloride is 0.57 degrees Celsius. So that is supplied. The answer that you will obtain will be in percentage weight per volume or grams per 100 ml of adjusting substance needed. So let's start off and doing the calculation. In terms of A, the freezing point depression of the solution that you'll have to make isotonic, that will be zinc sulfate. And from the information supplied, you can see that a 0.25% weight per volume solution of zinc sulfate depresses the freezing point of water by 0.022 degrees Celsius. So what you actually need to do is just substitute the values into the equation, and then you will get an answer of 0.865 grams. So you will need 0.865 grams of sodium chloride per 100 moles of solution to make it isotonic. And from the list of answers, you will see it is option B. The following example that we're going to consider is from the same domain and on the same competency standard. That will be competency standard 2.4. Let's start off with reading the question. A pharmaceutical company manufactures a drug containing 5.5 molars of sodium chloride. To what volume should 500 moles of the drug solution be diluted to prepare a 0.15 molar solution? Let's start off by identifying what type of calculation this is. And you will see in this calculation, you need to adjust the concentration of the sodium chloride from 5.5 molars to 0.15 molar. So this is actually from a high concentration to a low concentration, and it is in fact then a simple dilution that you'll have to do. For a simple dilution calculation, you can use the formula C1V1 equals C2V2, with the C's being the concentration of the respective solutions and V's the volumes. So substituting 5.5 molars for C1, and you have 500 moles of this solution, that will be V1. You need to dilute the concentration to 0.15 molar. And you need to know what the volume of this solution will be. And simple calculation, you will get an answer of 18,333.33 milliliters. From the list of possible answers, you will note that the answer is required in liters, not milliliters. So you need to convert the milliliter answer to liters, and that you do by dividing your answer in milliliters by 1,000, and that will give you an answer of 18.33 liters, and it is option B from the possible list of answers. The next question is from the same domain, domain 2. But this one is on competency standard 2.5, therapeutic outcome monitoring. So let's start off with reading the question. A 65 kilogram, 54-year-old male is admitted to hospital with a bacterial infection and requires a loading dose to treat the infection. What loading dose of medicine K is required to achieve an effective concentration of 7 milligrams per liter? The volume of distribution of medicine K is 0.25 liters per kilogram. In approaching this calculation, you will notice that this is a dosage-related question, and the volume of distribution needs to be calculated from what is given in terms of the information. You will note that the volume of distribution for medicine K is 0.25 liters per kilogram. Your patient weighs a total of 65 kilograms. So in order to calculate the volume of distribution for the drug in this patient, you will have to multiply the weight of the patient by the volume of distribution in liters per kilogram, and then you will get a total volume of distribution of 16.25 liters. And therefore, to get the required concentration of 7 milligrams of drug per liter of distribution, you will have to multiply the volume of distribution, which is 16.25 liters, by the required effective concentration of 7 milligrams per liter, and then you will get an answer of 113.75 milligrams. This will therefore be the loading dose needed to render an effective concentration of 7 milligrams per liter. From the possible list of answers, you will note again, this will be option B. Let's consider the following question. Again, this is on domain 2, but this one is on competency standard 2.6, pharmacist-initiated therapy. Let's start off. Let's read the question. Which one of the following is the correct amount of hydrocortisone 1% weight per weight cream and hydrocortisone powder required to produce 75 grams of a 3% weight per weight hydrocortisone cream? Please note in this calculation that you have at hand a 1% weight per weight hydrocortisone cream and you have hydrocortisone powder. And the question asks you to prepare a cream with 3% weight per weight hydrocortisone, and they ask you in what proportion should these two be mixed, meaning how much 1% weight per weight cream and how much powder would you need to prepare a 3% weight per weight cream. From this calculation, you have to note that we have a 1% cream to start with, and a concentration term that was not specifically noted, but you have to know, is if you have hydrocortisone powder, it means that it's only hydrocortisone powder. So the percentage strength of this will be 100%. So in fact, you have a 1% weight per weight cream and 100% weight per weight powder, and that you have to use to prepare a 3% weight per weight cream. So this is a typical example of an allegation calculation. When you approach an allegation calculation, there's always three concentrations at play. The concentration that you need and the two concentrations that you have to use to prepare the concentration that you need. And there's a specific way in which you have to write the concentrations in order to get to the answer. And I'm quickly going to use a pen and highlight that for you. The concentration that you need is 3% weight per weight, and that I will highlight in red, or rather encircle it for you in red. Let's use a different color pen to highlight the position of the two concentrations that you have to use to obtain the concentration needed. Let's use blue. 100%, that will be the hydrocortisone powder, and the 1% weight per weight cream that you have to use. So the two concentrations that you have to use are always written on the left-hand side. The concentration that you have to obtain, always in the middle. And then what you do, you subtract 100% weight per weight minus 3% weight per weight, render 97 parts, and then 3% weight per weight minus 1% weight per weight, render 2 parts. It's important to note that your answers that you get by the subtraction of the terms here is always in parts. Remember that. The only weight that was given in this calculation was 75 grams. And the 75 grams is the quantity of the 3% weight per weight cream that you have to prepare. So you can equate the 75 grams to the total parts. And the total parts you do get by adding 2 parts to 97 parts, and that will give you 99 parts. So if you know that 99 parts will therefore be equal to 75 grams, you can do a calculation and get the corresponding quantities of the 2 parts and the 1 part. Therefore, you will need 1.52 grams of the hydrocortisone powder, and you will need 73.5 grams of the 1% weight per weight hydrocortisone cream. So let's see if this is one of the options from the list of options that was supplied. You will note from the list of possible answers, the closest one will be option A, 1.5 grams of the hydrocortisone powder and 73.5 grams of the 1% weight per weight cream. So the correct answer will then be option A. Let's move to the next question. This question will be on domain 3, supply of medicines and medical devices, and it's from Competency Standard 3.2, Supply Chain Management. Let's start off with reading the question. A pharmacist needs 75 milligrams of piperazine for the preparation of a 1 ml ampule for injection, and only piperazine citrate is available. How much piperazine citrate does the pharmacist need to weigh to produce a total of 15 1 milliliter ampules? And then you will see in the question the molecular weight of the piperazine is given. That will be 86.14 grams per mole. The molecular formula is also given. Then the molecular weight of the citrate salt is also given, and you will see that's higher. That's 643 grams per mole. And then the molecular formula of the citrate salt is also given. I would like you to note that this question is on molecular weights. So we're going to use the molecular weights in this calculation. A further point that I would like you to note is that for your piperazine base, if you compare that to the piperazine citrate, you will see that there's 3 molecules of the base in 1 molecule of the salt. And I will quickly highlight that for you in the structure using a pen. Let's use the red color. You will see the base is that part. And if you consider the formula for the salt, you will see there's the base again. But in this case, there is 3 base molecules in the citrate molecule, in the piperazine citrate molecule. So this will have to be compensated for or considered in your calculation, and we're going to see how. First off, you have to prepare ampules of 1 milliliter. You have to prepare 15 of these ampules, and each of these ampules need to contain 75 milligrams of piperazine. So there's different ways in which you can approach the calculation. The way that's illustrated here is to start off and say we need 75 milligrams, and I've written it there, for each ampule. You need to prepare 15 ampules, so therefore we need in total 1,125 milligrams of piperazine base. However, as I've mentioned, you need to consider that there's, for each 1 molecule of piperazine citrate, there is 3 molecules of piperazine. That needs to be used in your calculation. So let's start off. Just getting my pen. 1 molecule of piperazine weighs 86.14 grams per mole. There's 3 of them, so you need to multiply that by 3, and that will therefore be equal then to 643 milligrams of piperazine citrate. You are in need of 1,125 milligrams of piperazine. So how much piperazine citrate do you need? That will be 2,799.22 milligrams. And from the possible answers, you will see that it is in grams. So you need to divide your milligram answer by 1,000 to convert it to grams. And that is equal to approximately 2.8 grams. And from the list of answers or possible list of answers, you will see that it is option D. Let's move to the next question. It's on the same domain, domain 3. However, this is on competency standard 3.5, and this will be medicine compounding. Let's start off reading the question. you need to prepare a sufficient volume of 1 molar hydrochloric acid to be used to produce a buffer solution. Calculate the number of milliliters of 32% weight per weight hydrochloric acid that is required to make 75 milliliters of a 1 molar hydrochloric acid solution. And then there's certain info given. The first being the molecular weight of hydrochloric acid, which is equal to 36.46 grams per mole. And what's also given is the density of the 32% hydrochloric acid solution, that is 1.16 gram per milliliter. Now, before we're going to take a look at the memo, there's certain aspects that we need to address before we start to take a look at the memo. First off, this is a typical example of a complex dilution. You're going to use both molecular weight as well as density. And the concentration term that is used here is molar. So you have to know what molar stands for. If you don't know that, you won't be able to do the calculation. So you have to be aware of concentration expressions and the definitions applicable to those. For this question, we're going to work with molar. That will be moles of hydrochloric acid per liter of solution. So let's start off and let's take a look at the memo for this question. Again, there is more than one approach to this question. I'm going to explain the one that's on the slide. As I've mentioned, you need to be aware that you're going to use both density and concentration. And we start off with 1 molar. As I've said, it's 1 mole of hydrochloric acid in 1 liter of solution. You don't need to prepare a liter. You only have to prepare 75 milliliters of a solution with a strength of 1 molar. So if 1 molar equals 1 mole, that will be 36.46 grams of hydrochloric acid in 1 liter of solution. How much hydrochloric acid do we need in 75 moles? 75 moles are equal to 0.075 liters, and you get an answer of 2.7345 grams of hydrochloric acid needed. Let's quickly encircle it. So this is what we need in terms of hydrochloric acid in weights. Now, the question that you need to ask yourself is, where do I need to get it from? You need to get it from a 32% weight per weight hydrochloric acid solution. Now, 32% weight per weight means you have 32 grams of hydrochloric acid in 100 grams of the 32% weight per weight solution. You're only looking for 2.7345 grams of hydrochloric acid. So how much of this solution do you need to weigh off? And then you will get 8.545 grams of the 32% weight per weight solution. However, you will note from the possible list of answers or the possible answers, they want the answer in milliliters because the 32% weight per weight solution is a solution. So you're going to measure it off in a measuring cylinder, for instance. So you need to convert the 8.545 grams to an equivalent volume. And the moment you need to move from a weight to a volume, you're going to use density. That's why the density of the 32% weight per weight solution was given. So this is the calculation or the formula applicable. Volume equals weight over density. You know that you need to have 8.54 grams. The density is 1.16, and then you get an equivalent volume of 7.5 milliliters. So if you take 7.4 milliliters of the 32% weight per weight hydrochloric acid solution and you dilute that to a volume of 75 moles, you will have in fact a 1 molar solution of hydrochloric acid in water. Let's see if this is one of the possible options in the list of possible answers. Moving back to the question, you will see that 7.4 milliliters is in fact one of the possible answers, and it is option A. This brings us to a close on examples of the type of calculations that you can expect, and we wish you, or we would like to wish you well in your preparation for the pre-registration exam. All the best.